So the dimension of hidden layers is a lot higher, but we're using fewer parameters. So let's see how the information actually is propagated from the input to the hidden layers. In a fully connected architecture, there's a global information gathering. Now, as each of these pixels is connected to all of the neurons in a hidden layer with different weights, remember, the information across the n0 times m0 pixels is gathered into this d1 dimensions. So the entire image needs to be represented in a single vector here. In a convolutional architecture, things are different. Now, if I look at the neurons at a given pixel in a channel, and remember they're D1 channels, so let me actually stack this as a tensor like this, and look at the vector here in the first pixel in the channels. Now, these neurons gather information only from a sparser location, only a smaller location in the image. These neurons, they gather information from a different location in the image. And likewise, each of these neurons in these channels, they gather information from a local area, of local neighborhood in the image. So notice that I don't only use a small vector, I use a set of vectors, and each of these vectors, they're responsible for gathering information from a local neighborhood. So this tensor, this hidden layer, is much larger dimensional. And the information that's gathered across the different pixels in these channels, they basically gather local information. So to retain a similar level of information, you would need a much larger layer in a fully connected network. Here, I don't need a very large D1 to retain the same amount of information because each D1, each vector here, is responsible for gathering information in a much smaller area. So that's a big gain. So let's look at the layer size and number of parameters. So we looked at it from the input to a first hidden layer. Let's look at what happens in the intermediate layers. So we're now connecting a hidden layer L-1 to a hidden layer L. So in L-1, I have D sub L1, L-1 dimensions. And in the next layer, I have D sub L neurons. So the layer is D sub L dimensional. The weight matrix that connects them is therefore D sub L times D sub L-1 dimensional. In a convolutional layer, my network is composed of these set of channels as layers. So L-1 layer is D sub L-1 channels, and each channel has this many neurons. So the total dimension for the hidden layer L-1 is D sub L-1 times N sub L-1 times M sub L-1. If I look at the next layer, I have a similar structure. Now the dimension is D sub L times N sub L times M sub L. Now each of these channels is connected to each of these channels with a different convolution kernel. So my weight set is composed of these different kernels, and each of these, as I said, channels are connected to the next layers, each channel with a different kernel. So therefore, I have D sub L-1 channels in the first layer, D sub L in the second layer. So in total, I have D sub L-1 times D sub L convolution kernels. So it's very similar to the weights here. Instead of a single scalar, though, I have a kernel. So the weights of a kernel can be k sub 1 times k sub 2. So the number of elements, number of components in a kernel. So if you consider the larger layers, due to the sparser connections, this will end up having much fewer number of parameters than this guy. Because to be able to retain the same amount of information here, I need much larger hidden layers. We didn't really talk about the channel size, but actually the channel size is very much linked with the kernel size and the type of convolution that we're applying. Now, we basically looked at this when we described the convolution kernel. We basically took a 5x5 image and convolved it with a 3x3 kernel. Now, in that case, we saw that actually the size of the output was not the same as the size of the input. The size of the output reduced to 3x3. Why does this happen? Now, when I do a convolution, when I place the kernel inside the image, there is no problem because for each of the kernel weights, there is a corresponding pixel. So I can multiply and add. But when I place it at the boundary of the image, I have a problem. If I, for example, place the kernel here, so I see that there are 4 pixels that overlaps with the kernel, but then there are these 5 kernel weights that actually don't correspond to a pixel. So there, the convolution operation is not really valid. So if these out-of-boundary values are not defined, then I have really 2 options. Either I perform valid convolutions, meaning that I can only evaluate the convolution when all elements are well defined. In other words, when there is a pixel corresponding to each of the kernel weights. Or yet in other words, when the kernel is fully overlapping with some set of pixels. So I can only place the kernel here, in this 9 pixels in that case. Or I can do padding, and I can say that even though these pixels are not defined in the image, let me use a value for them. For instance, let's use U0 for them. Then actually the convolution will be defined even in these areas. Now, the valid convolution, if the kernel is centered, meaning that if I assume the center of the kernel is W0 and 0, then the convolution can only be evaluated within the red area. So I can only put the center of the convolution at most at this location, in the top right corner at this location, bottom right corner here, and bottom left corner here. So it's well defined whenever I place the kernel inside this red area, and it's not well defined whenever I place the kernel in these boundary pixels, if it's 3x3. That means that I will lose a pixel at each end of the picture. Now, if the kernel is centered at its top left corner, then a similar thing happens. I can now place the kernel only in these green areas and not on these boundary pixels, the final 2 rows and 2 columns. Again, I lose 2 pixels, but now at the bottom and the right of the image. Effectively, the layer size, the channel size, decreases if I use valid convolution. That depends on the kernel size. So if my kernel is K1 times K2, then I can actually compute the size of the channel based on the kernel size and size of the previous channels. Specifically, the size of the channel in the next layer will be related, such as M sub L will be M sub L minus 1 minus K sub 1 plus 1. And likewise, N sub L will be N sub L minus 1 minus K2 this time plus 1. So when the kernel is 3, that basically means 3 minus 3 plus 2. So this becomes minus 2. So I will lose 2 pixels. And that's what we've seen here. And I will lose 2 pixels on the vertical direction as well. When K is something else, if we assume K is 5, then minus 5 plus 1, that will make minus 4. So I will lose 4 pixels in the image, in the channel. And likewise, the same thing happens in the vertical direction. You can imagine kernels of different sizes in the vertical and the horizontal direction. Then the amount of pixels you will lose as you go through the channels will be different as well. The alternative is to use the padding. So you can actually imagine the same padding. You can pad the image on the boundary so that the channels will have exactly the same size across layers. So if I think about this image, and if I think about the 3x3 kernel, that basically means that I pad the image with the boundary pixels that all have, for instance, 0 values. So this time what happens? I had the channel size in my previous layer. I basically increased the channel size by adding 1 pixel across, so 2 pixels in each direction, so one on each side if my kernel is centered. Then if I do the convolution, I will basically, the k1 minus 1 and k2 minus 2, minus 1, this should be, will basically die out. So this should be minus 1. Let me actually correct it even now. So this should be 1. And I will correct it in the PDF and the PowerPoint I put online. Good. Now, where you pen depends on the center of the kernel. And commonly you would use centered kernels. That's kind of the common practice. So padding around the image, as shown here, is the way to go in this case. Now, the value you pad is a parameter. It is customary to use 0, not to complicate things. But you can also imagine using symmetric padding, for example, using the same values here for here, or different padding strategies. Now, we've seen the padding, we've seen the valid convolutions, and the links between the channel sizes. So maybe we can ask it now, we were ready to answer a question on the number of parameters. So let's assume that we have a classification network with 16 possible output classes. How many parameters are in the following fully connected network, where each arrow is a fully connected link? So I basically have a 64 by 64 image, and I connect it to a first hidden layer of 256, then 128, and so on, until it goes to 16 channels. Now, each connection will have a weight matrix and a bias. So I will leave you to compute the number of parameters here. Next, you can ask a similar question: how many parameters and how many hidden neurons in each layer in the following convolutional neural network, where double arrows are convolutional links with 5 by 5 kernels and using valid convolutions, and arrows are again fully connected layers. And once again, you can imagine that there is actually a weight bias vector, and here the bias vector, basically I would add a bias to all, so one bias per channel, meaning that I would have 16 biases here, and here I would have one bias per for the entire thing. So I would basically have, so one bias per the entire thing. So I would basically have one bias value here. No, 256 value here, sorry. 256 bias values and 16 bias values here. So I will not give the answers here. I will leave you do the math. And this is, by the way, a very similar questions like this appeared last year. So you can actually solve this quite easily by looking at the slides that we've seen so far. Now, this basically dealt with the number of parameters, and I hope I convinced you that the number of parameters in a convolutional neural network is much less than that in a fully connected network when we're dealing with images. The next thing we discussed was this aggregation of local features, or basically the hierarchy of local statistics. And I think we've seen it quite a bit so far as well. So a convolutional neural network basically aggregates the local spatial statistics. So if I look at the connection between the input image and the first hidden layer, I see that the representation of a given channel pixel in the first hidden layer basically has information about a certain area in the image. Now, if I connect the first hidden layer to the second one, here a local area of the first hidden layer is represented. Therefore, this representation has access to a larger area in the image. So as I go through the layers, I basically aggregate local statistics. So I basically have first level representation here that only represents a certain area in this image. That representation is now used to create another representation that has access to a larger area in the image, and so on. And as the layers progress, more global information is encoded in these representations. Let's see a very simple example how this works. So here I have the input image. Let's assume that my first layer computes the derivatives in the vertical and the horizontal directions. Okay? So the x derivative and the y derivative. And I'm showing only the results after the nonlinearity with a rectified linear unit. Now, let's assume in the second layer I do the same operation. So I have x derivative and y derivatives. And now this time it will be applied to both this guy and this guy. Now notice something very interesting happens. I basically have now weighted sums of the second order derivatives. And here I was highlighting edges normally, as expected. And here I basically have a larger level of information. Here, for instance, I highlight corners, and here some other level information and so on. So it looks like as I aggregate more information, here I was actually looking at edges and corners. And if I were to go even deeper, that would actually look in combinations of corners and then combination of those and so on. So basically aggregating local information and always looking at more and more complex structures in the image. The second thing, the last thing we talked about the problem of fully connected layers was the translation invariance. Now, the translation invariance is not native to fully connected networks. As we discussed, given these two images, the vectorized representations of these images will be very different. Now, that means the representation in the first hidden layer will be very different, and so on. So these images will most likely lead to very different activations in the hidden layers, and the rest of the network will see very different activations. So the results will be very different. However, in most vision applications, these images should lead to almost identical outputs. Actually, there are some, we can discuss the applications where they should lead to identical and different outputs. When I talk about recognition or detection, so recognition meaning that what is the number in this image, or detection is there a 2 in this image, then the results of these images should be identical. But I can also talk about different outputs, for example, the localization and the segmentation. In that case, the results will be different. So I actually need architectures that can deal with both of these cases. And fully connected layers, it will be very difficult to deal with the identical outputs. And it will be even difficult to deal with the different outputs, because even there is a difference here, the output is somehow related to the translation of the input. In other words, actually, if I translate the input by this much, I would expect the output to be translated by this much in these tasks too. So in a sense, they're not translation invariant, but those tasks should be translation equivariant. Now, translation invariance actually is not, as we said, not native to fully connected layers, but it is possible to teach a fully connected network to be invariant to translations. How? Well, you can basically show the network lots and lots of translations of a certain image and ask the network to give you exactly the same output for all of them. So this corresponds to data augmentation in a sense. So basically, by showing examples, you teach the network to be invariant, or you teach the fully connected layers to be invariant to translations. And we've seen this to some aspect in the past as well, when we were extracting features, for example, that were not invariant to certain transformations. Our strategy was to show examples of such transformations and ask the features to be similar. This is obviously not the most elegant way of doing translation invariance. Convolution operator helps quite a bit in this case. And it doesn't help because it's translation invariant, but it helps because it's translation equivariant. So what does this translation equivariance mean? Equivariance means applying a transformation to the input yields the same results as applying the transformation to the output. So if I have input x, and if I transform it with a transformation t, and if I apply the network, that should be the same as applying the network to the image and then applying the transformation to the output. And convolution is linear shift invariant. So it has translation equivariance, it's shift invariant. To basically prove this very simply, we can look at we can apply, for example, the derivative operators, and we know that they're convolution operations to these two images. And we notice that the outputs They're not exactly in the same place, but the outputs are almost exactly the same in both of these cases. They might be different due to discretization, but ideally they're exactly the same, just the translated versions. So you can imagine that instead of translating the input, I could have actually computed the convolutions and then translated convolutions. So they're the translation equivariant. Now, it doesn't mean that that's translation invariance. Actually, convolution layers, they do not have translation invariance. Again, we can actually think about in what applications do we need translation equivariance and invariance. And we've already seen that translation equivariance, this property is actually quite useful when I'm talking about segmentation and localization. And translation invariance would be quite useful if I talk about recognition or detection. And both the equivariance and the invariance are very difficult to achieve with fully connected layers, while equivariance is already guaranteed with convolutional layers, and invariance actually can be achieved with additional components. Now, the convolutional layer is a great idea, but there is actually a problem. So first, as we said, in order to achieve translation invariance, we need some more thing in it. And related to this, the dimensionality reduction requires many, many parameters. So assume that we have this image and assume that our goal is to do recognition. Now, we can use convolutional kernels of size 5 by 5 with valid padding in a recognition system. So the output, again, in a recognition system should be of size, if I'm actually looking at only a binary classification problem, should be of size 1 by 1. If I think about the 10 class classification problem, should be 1 by 10. So going from 128, I have to go to 1 by 10. Now, to do this, this is possible, but I would need many, many, many layers. So if I use 5 by 5 convolutions, in the first layer, I drop the image size from 128 to a channel size of 124. If I apply it again, the channel size will drop to 120 and then 116 and so on. Now, obviously, there is one way to basically reduce this dimension much faster, which is to use larger kernels. But then larger kernels means larger number of parameters. So I basically go down to the same drawbacks that I had in the fully connected layers. There is actually another way to do this. Now, there are actually quite a number of ways to do this, and we'll see two of them. One of them is strides. So in a normal convolution, you only move one pixel in each direction, and you wouldn't skip any pixels. So first you would compute it here, then you would compute the convolution here, and so on. But there is no reason why you shouldn't skip pixels. So you can shift by 1, but you can actually shift by 2, by 3, by 4, and so on. So you can decide to skip several pixels while shifting your kernel. Instead, for example, you can skip 2 pixels, so you can compute the convolution here, then here. Or you can even take a stride of 3. And this leads to a tremendous reduction in channel size, because the number of outputs that I will get are basically halved now. Specifically, if you want to compute the number of channel size with a stride of S1 or S2 in the horizontal and the vertical directions, the channel size with valid convolution decreases like this. So they really decrease as you would like divide by the stride number. So that's pretty good. So assume let's look at this again. We use a convolution kernel of size 5 by 5. Now we again do valid convolution, so no padding, with stride 2 in the recognition system. So now, in the original version, when we didn't do stride 2, but we basically used normal convolutions, we went from 128 to 124 and so on. If we now use stride 2, instead of going to 124, we now go to 62. And then we go to 29, and then we go to 12. And already in 3 layers, I dropped the channel size to 12 by 12. So that's actually pretty strong. The dimension drops very quickly, and the rate of drop will be faster if you increase the stride size. So instead of using 2, if you use 3, then it will drop even faster. Now you lose information, and higher strides means higher loss of information. And you do not necessarily gain in translation invariance, but you have now the capacity to reduce the size quite a lot. And when it's used, and if used, it's commonly used with a stride number of 2 in all directions. Now, there's actually another strategy to reduce the dimensions faster and allow us to gain some level of invariance to translations. And that's what's called pooling. Now, pooling layers conceptually work something like this. And there are multiple ways, but let's look at the max pooling. So I start with an image again. Right? Now, if I want to pool, I do something very similar to convolution. So I basically look at a certain area in the image, but instead of applying convolution, I basically compute the maximum value in that area and only retain that value as I go to the next layer and discard the rest. So more in detail, let's see it here. So pooling it basically pools the information in a large neighborhood like this with a single value. So it summarizes the information. And it will be applied to each channel separately when you add the pooling layer. Now you can have multiple pooling strategies. You can have, for example, maximum pooling, max pooling, which basically means that I will look at the activation values here and I will only retain the maximum value here. So in this case, in this area, the maximum value, for instance, can be 617. You can alternatively look at also the min pooling, so basically retain the minimum value. And both of these are nonlinear operations, so they're almost like rank filters or median filtering, one be one of them. You can also think about doing average pooling, like the linear operations as well. Max pooling is the most commonly used version, and you can imagine that max pooling is roughly very similar to min pooling. So you represent, in a max pooling operation, you represent the entire region with the neuron that achieves its highest activation. And this leads to a partial local translation invariance because basically wherever that 617 is, it will be retained. So it's kind of invariant to where the 617 is in this patch. And the pooling will not change even if its location changes. So it doesn't lead to complete translation invariance as you can imagine, but to some partial translation invariance that ends up being extremely useful. Now, this is actually often applied with strides equal to the size of the kernel. So you wouldn't do pooling here and just shift this path just by 1 pixel, but you would shift it by, in this case, 3 pixels. And again, this leads to a substantial dimensionality reduction. When we do pooling, basically, if the kernel size is 2, and if I apply pooling with strides 2, then it simply halves the image size. And as the size of the pooling kernel increases, the reduction will also increase. And it's quite nice because I basically add another level of nonlinearity in the system. So I basically achieve nonlinear dimensionality reduction when I do pooling. Now, only the most prominent activation is transmitted to the next layer. And there are actually more advanced pooling mechanisms that exist, like the capsule nets. But the essence is the network weights in the previous layers, they arrange themselves such that the most important information that should be passed to the next layers for a certain task is captured in the most prominent activation. So for example, if I apply pooling to here in this image with a 5x5 kernel and strides of 5, then I simply take this 10x10 image and represent it simply by 4 values. So the dimensional reduction is huge. Now, actually, you have all the components you need for a recognition system. You have the convolutional layers, and you know what convolution is, valid convolutions, padding, and you have the pooling. So actually, now you can already build a very successful recognition system like the one here. So you take the image, you first do some convolutions and get channels, you do pooling, you apply another convolutions and pooling, and so on and so forth. So basically, successfully applied convolutions and pooling. And now, if and when the size of the channel is reduced enough, you can basically now vectorize it and simply use a fully connected layer to summarize all the information in the image to, for example, decide whether the image you see has a car in it or not. So the network architecture for a simple object recognition system would then look like this. You have the image that followed by convolution, followed by nonlinearity and then max pooling. Same thing happens and again and again and again. And when the channel size is small enough, you simply vectorize it and then use a fully connected layer to basically achieve your final task outputs. For example, the class probabilities in the final layer. And it's important to use a fully connected layer here for the task of recognition, because if I want to recognize an object in this image, I basically need to have access to all the information in it. And this fully connected layer ensures that each of these decisions has access to all the information in the image. So somehow these layers do aggregation of local statistics, and then only the remaining information is fully vectorized and connected together. And at the end, I basically use the same mechanism that I used before. For instance, at the final layer, I have a fully connected layer like the one we saw last week, and I basically feed the outputs to a softmax function to get the probabilities for a recognition system. Now, putting them all together, I basically have the convolutional neural network. Final layer is the output. I have the softmax and so on. And how do I train it? Well, the same way as I trained fully connected layers. The information flows forward as I do a forward pass to do prediction and inference. And when I want to train it, I simply compute the errors at the output and propagate the errors backward, and each time update the weights of each layer. Weights, in this case, would mean the convolution kernels. I need, again, a cost function, and you can imagine using any cost function that we've seen last week, for instance, the cross entropy in this case, and I basically do optimization like I did before. And the optimization basically means that I want to optimize the cost function between the labels in the training set and my network's prediction, and I simply tune the network parameters. In a convolutional network, that basically means the kernel weights, for example, using a gradient-based optimization. And once again, as I go forward, the information is progressively moves forward, and as it does, I aggregate spatial information more and more until I reach this point when I vectorize, and I simply combine all the information together with a fully connected layer to go to the output to reach a global decision. So the local features in these layers see only parts of the image, but as the features get aggregated, I see more and more of the image to basically create these representations, and finally everything is put together. So the last layer sees the entire image. Okay. And believe it or not, these are all the essential components to build a state-of-the-art, powerful convolutional neural network that will achieve very good results in, for instance, the ImageNet challenge. And with that, I stop this part and I will continue